Hello, everyone. Sorry, I'm a bit late. I put a couple of references on the chat that I think we're going to be looking at today. First of all, let me make sure that everyone can hear me. Can someone?
Yes, yes,
Thank
Joseph.
you. And can you see the screen that I'm sharing?
Yeah.
Yep.
Okay, great. So um, there's a couple of references for BERT that I think I'd like to look at and I'm planning on having two classes on or two sessions on BERT. This one, and we'll cover Jay Alamar's blog, which is really good, a good introduction to BERT. And then next time, hopefully, we'll cover a more hands-on tutorial that from Chris. Let's see, what's his name? Chris McCormick, and that'll be the BERT fine-tuning tutorial with PyTorch. So that's much more in depth. But the one that we'll cover today is just going to be very superficial. It's just going to give sort of a big introduction to a big overview of all the modern developments in NLP associated with BERT and Elmo and ULMFit and OpenAI. So that's what I plan to do today. I'm just learning this stuff, and I'm probably many of you, maybe even most of you, know more about this than me. So at any point during this discussion, feel free to step in, and we'll be glad to make use of your understanding of things. So first of all, let me get rid of some of the background noise by closing a window. Yeah, unfortunately, there's a guy that does landscaping across the street from us every Saturday morning at 8 o'clock. So I have this background noise. Hopefully, most of it's eliminated. By the way, did you hear that background noise before I closed the window? It was really,
No,
yeah.
no, it wasn't that much. No.
Oh, good. Okay, because it was really bad for me. I could barely even hear myself think, but I have a noise canceling mic that I hoped was working well. So apparently it is.
It is working.
Okay, terrific. All right, so let's dive into this thing. So Jay Alamar, the guy that we know about from his uh, tutorial on transformers, has written another tutorial on BERT, Elmo, and company. So he talks about the ULMFit, OpenAI, Elmo, and BERT, and this is sort of a very superficial introduction, but I think it's really useful as well. So let's just go through it. First he shows, and this is a really interesting thing for me, at least for anybody starting up. He shows what BERT can do, what kind of things it can do. So, the application that he shows here is that BERT can do spam detection. So you give it two sentences, and then it give it a list of sentences, and then it can classify them as either spam or not spam. So, and he shows that this is done in two steps. First, it trains on large amounts of text and so on, and then it takes a tremendous amount of processing power to do this. But then you can download the pre-trained model that from the left-hand side, and then you can use that model and use it directly on your classification problem. Okay, so he says that BERT is building on a bunch of previous ideas, and he lists them: Elmo and ULMFit, and the OpenAI transformer. So then he goes into some details on those three things. But first, let's look again at sentence classification tasks. So you give it a sentence, give it two sentences. It goes through BERT. At the end of BERT is just a classifier, which is a feed-forward network plus a softmax. and then out comes the prediction. Note that since we have a softmax network, we can make multiple label predictions, so it so it doesn't just have to be a two-class problem. Okay, so let's see. He talks about pre-training and the ULM fit. Before we go on, he talks about different kinds of problems that are related, that are similar to spam classification. Sentiment analysis, positive or negative. Like reading a movie review and deciding whether it's a good one or a bad one. Fact checking, reading an input sentence and then deciding whether it's a claim or not a claim. Maybe that's for an insurance. I'm not sure what that would be for. And then he talks about full fact. So fact checking tools. So BERT has applications in fact checking. So in the paper they talk about two models. One is the BERT base and one is the BERT large, and they're basically the same thing except they have different sizes. But the base model was built in order to do a apples to apples comparison with GPT-2, with the OpenAI's GPT-2 model, and basically showed that it could crush GPT-2 in a whole bunch of different tasks. So once it establishes that it's better than the best state-of-the-art model, then they take advantage of the fact that they can access all kinds of compute power. They build this huge model, and then they turned it loose on a bunch of tasks and just blew away all existing records. So let's see. An interesting fact that they say is that BERT is just a stack of encoders. So we learned about the attention model, and we learned that it has two parts. There's the left-hand stack has the encoders, then the output from those encoders goes into a decoder stack, and BERT is just the encoder part, or is just built on encoders. Let's see. So this is another view of the classification tasks where you have a bunch of words going in, and the sentence lengths are limited to 512 tokens. Sentences going into BERT, out comes the encoding with this blue thing here, and then it goes into a classifier, which is just a feed-forward neural network with a softmax, and then out comes the classification. Let's see. It talks about this. We've already seen this, parallels with convolutional networks. We've seen that before, where you have a convolutional network, and then the last layer is a classification layer. So remember the FastAI dog and cat or dog breed classifier. It was the same thing. We had this CNN layer. We had a bunch of CNN layers, and at the end of that, it had an output with the number of outputs, number of classes that we wanted to classify. So if we wanted to classify, 37 dog breeds, we'd have to have an output with 37 elements in it, and then that would go through a softmax, and then it would give a classification scheme. Okay, so now he walks away from BERT for a moment and talks about Elmo. But first, let me pause here and see if anyone has any comments, because I know that probably all of you, have more knowledge of this than me. So I'd like to make use of what you already know. So anybody that wants to step in here and make a comment or any interesting comments about BERT. Okay, then let's move on. Yes.
No, the earlier comment you made about BERT and GPT-2. I think it was GPT because
Oh,
BERT
before
came in.
GPT-2.
Yeah, BERT came towards the end of 2018, I think, and I'm not completely sure about this, but it might have been GPT at that time.
Yes, I think you might be right. So this is what they call the OpenAI transformer. I think that's what they're calling GPT. So it's GPT, not GPT-2.
Yeah.
Yeah, thank you. Okay, so back. So now we're going to talk a little bit about.
And if I may, another comment.
Sure.
The main reason why BERT outperforms GPT is because GPT is a left to right language model. So it's a traditional language model. So it's left to right. So it only sees words that are before it. And whereas BERT is a fully attention model. I mean, it's just based on attention. So it's able to build, encode the words by attending to words that are on either side of it. So that's why, as an encoder, BERT is much better when used for other tasks
Hmm.
than compared to
Yeah.
GPT.
Yeah, I know that that the B in BERT stands for bidirectional. So yeah. Um,
So, a question, Gautam, is a GPT, as you said, it is a left to right, but it is it's based on the RNN LSTM, or is it based on the attention or a transformer?
That is a good question. I'm not sure, but it's still, even if it's attention based,
Yeah,
the words that are right of it is probably masked out, so it cannot attend to that.
correct.
yes.
Yeah.
Yes,
Correct.
that's right.
And I think that's the major difference where I'm not 100% sure, but I think its attention, it
Yeah.
uses the transformer. But you're right that the BERT is trained on the two tasks where it
Yeah.
can look at the word a sentence as a whole rather than just from the words which are just before it, not forward, something like that.
Yeah.
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 So is the difference the way the two models are trained then the the GPT model and other language models before it were just trained to predict the next word, so it wasn't so they weren't allowed to look ahead because that would be cheating, right? But but BERT somehow finesses that rule, and I'm not understanding quite yet why it works. I mean, I know that the two, as Dinesh mentioned, the two tasks that BERT trains on, which we'll see below, are one, a masked attention model where it's given a sentence with words that are, with some of the words masked out, and then it's trained to actually fill in the blanks. It's actually trained to guess those words that are masked out. But in doing so, it's allowed to look from both left and right because I guess there's no reason why that particular task can't, since they're not trying to predict the next word, then it's fair to let it have bidirectional attention. So I think that's the first task that it's trained on. And then the second task that it's trained on is actually sentence prediction, where it's given, and we'll see that again below, where it's given pairs of sentences, and 50% of those pairs, the second sentence is actually the one that follows the first sentence the in the training corpus. But in the other 50% of the sentence pairs, the second sentence is just a random sentence, so it's not connected in any way with the first sentence. And so BERT has to learn um, how to figure out whether in a pair of sentences, the second one is the right one that follows the first. So that's an interesting, that's what it's being trained on, and that's not the same as how ordinary language models are trained. So maybe that's the reason why it's makes better use of this bidirectional attention.
Also,
No,
was there any mention of, sorry, was there any mention of how they compared BERT and GPT on what tasks specifically?
yeah, that's in the paper.
Okay.
And let's see, there. there's another blog here. You're seeing what I got on my screen, right? This is the Alamar, the J. Alamar blog that we're
Yes.
making our way through. Okay.
Yep.
There's another one, and if I switch to it, you should be able to see it as well. Did you see what I switched to?
Yep.
Okay, understanding BERT part 2. This guy goes in a little bit more detail about how BERT is trained, and he talks about how GPT is trained, and then he reviews the transformers a bit. But then in the end, he actually goes through and shows all of these tasks and shows the results from all the different tasks. So here you see glue and squad, which we're familiar with, named entity recognition, swag, I don't know what swag is, situations with adversarial generations, and then ablation studies. These follow the sections in the paper. So the BERT paper is about half of it is devoted to explaining all the experiments, and section 4, in fact, is experiments, and it goes through glue, squad, swag, and ablation studies, just this stuff. So this is a good review of the tasks in this blog, Dissecting BERT. But you can also get it probably from the horse's mouth by just going to the paper itself, because that part is just not heavy reading. It's just it's just reading the results of the tests, and maybe if we have time, maybe we'll just go through that at the end. But well, maybe we can just go through it now quickly, since you asked. So going back, testing and results. So here it says BERT base and BERT large, and then OpenAI GPT, as Gautam said, not GPT-2. BERT base has exactly the same parameters as GPT. So there are 12 layers. There are 768 hidden. The size of the hidden layer is 768. And L and so L is the number of stacked encoders, H is the hidden size, and A is the number of multi-head attention layers. So this is, we saw that in the original transformer model. I think they just used 8 of these, and I think they used 760. They used maybe 512 as the size of the hidden layer, and I don't remember the number of stacked encoders. If anybody remembers the number of stacked encoders, just for comparison, for the transformer model, the original one.
I think in transformer they did 8, but
so this 8. This was 8. 5, 12, and 8.
Transformer, yeah. But I think when they did the BERT, they were comparing with the GPT.
Yes.
So BERT and GPT should match.
Yes. So BERT base is designed to match GPT, so they could actually do a head-to-head comparison. So then he mentions the 2 clear conclusions from the BERT paper is that BERT base beats OpenAI GPT, and BERT large beat BERT base, which of course you expect since it's almost twice as big. But the idea is that the architectural modifications on that they made on OpenAI GPT, and I didn't realize that the BERT authors were actually basically their goal was to improve on GPT by adding this bidirectionality piece. So the conclusion of the paper is bidirectionality really helped a lot, and so now we can compare some of the results in the glue, the 8 glue classification tasks. And I don't remember exactly what these all are, but you can see that BERT base here is 79.6 on its average, and OpenAI GPT is 75.2. So there's a clear, it beat it by a lot. And in the squad class, in the squad task, we have, let's see, BERT base. Do we have a comparison with?
I think interestingly, one of the tasks, if you go up a little bit, Joseph, is the Quora question here. The QP stuff.
Which one is that?
That's the QP, I think.
Ah, okay, right here, this one. Yeah, so OpenAI got 70.3 and BERT-based got 71.2. And before OpenAI, it was 66.1, so there was a huge improvement from OpenAI, and then a small improvement over OpenAI by BERT. And of all of these tasks, it looks like the biggest improvement was from BERT came on this one. Well, yeah, 45 to 52. So I don't know what this COLA, does anybody know what this COLA task is? Anyway, that was a huge improvement from 45 to 52. And then another huge improvement is on this task, RTE. I'm not sure what that is, but it went from 56 to 66. And then another huge improvement from BERT large. So, yeah. And then some of these tasks, I don't see an OpenAI benchmark to compare with. Let's see. Named entity recognition, we're comparing with Elmo, and I don't know what CBT is. And swag, I'm not sure what that task is, but again, we don't have a benchmark from GPT. But this was a huge improvement over whatever this previous record was. Anyway, okay, so this is in this paper, in this blog, they review some of the results, but probably you'd do better if you're interested in the results to go to the original paper and have a look at what they say. There's just a few pages where it's a very short paper, the BERT paper, and in the last maybe four pages or so, maybe a little more, yeah, 4 or 5 pages, they discuss all of these tests. So that would be a good place to refer. So let's go back to, if no one has any further comments on this, if you do, welcome. Okay, so let's go back to the J. Alomar, where we're now going to have a look at Elmo. So he starts talking about this new age of embedding, and he talks about the word2vec and the glove, which take words and train these embeddings on them, train networks to find embeddings on them that can then be imported as is in further modeling, or you could try to improve on them. But since they were processed with a large amount of compute power, it's probably for a lot of tasks, it's good enough just to adopt them as is. But then Elmo came in, and its main contribution was that this is a good cartoon that says it. Elmo actually changes the embedding of the word with respect to the context that it's in. So it's called contextual embeddings. And so the embedding of a word wouldn't be the same from task to task. The embedding of the word would depend on what task you're trying to solve. Or actually, not what task you're trying to solve, but what sentence it's in. So it changes with every sentence. So here, the cartoon says if you want to find the embeddings of a word, give me a sentence in which it's used. So he gives the sentence, and then he says, okay, now I can tell you the embeddings. So it says here, instead of using a fixed embedding for each word, Elmo looks at the entire sentence before assigning a word. So input sentence Elmo. Elmo then finds the right embeddings for the word. So this shows the architecture of Elmo. It has two LSTM layers, and then these little things are the hidden layer outputs. These little things coming off the head, off Elmo's head, are the hidden layers. And remember, in an LSTM, the hidden layer gets passed on to the next one. But I guess what he says is that they keep those hidden layers around because they use them. They come in handy later. Um, so embedding, ordinary embeddings go in, and then out comes sentence embeddings or embeddings based on the sentence. So you just take these two LSTM layers. The output of the second layer goes into a feedforward neural network plus softmax, and then out comes the I guess you can get a score for a whole list of all the English vocabulary words. I don't know, 30,000 of them, and it gives you a score. Which one is the most likely to be? Which one it's most likely to be? The next word is most likely to be. So let's see. Let's see the hidden state of. Okay, so. So this one, I guess Elmo is using a backward language model and a forward language model and combining them. So here's the sentence going in. The forward language model predicts, I guess, I'm not sure what it's trying to predict. Is it trying to predict an embedding? Yeah, it's trying to predict an embedding. It's trying to give an embedding. So you get an embedding coming from the forward language model. You get a different embedding coming from the backward language model. And then you concatenate all the hidden layers. You can see these are the hidden layers. So this is dark red and light red. The dark red is the LSTM layer 2 hidden layers, and those are concatenated with the backward language model second layer. So that gets this one. And then the LSTM number 1 from the first layer, its hidden states are combined with the hidden states from the backward model LSTM layer 1, and that's this light red and light purple. The original sentence is in green. And then, yes.
I believe the task is just language model predict the next word.
Okay.
And the hidden state is like a, it's like a proxy for the embedding. So if you want to get the embedding of the word stick, you would just take the hidden state of the word stick from the forward language model and the backward language model, and then you just append them. I believe that's how Elmo works. The task is the same language model. So when you train it
Okay.
on language model, the hidden state kind of represents an embedding for that, a contextualized embedding for that particular word.
That's the output then of the.
No, the
That's
output is the next word of your sentence, whatever it is. But the model as a whole is just a language model which predicts the next word. So if you input your current sentence to this model, and if you want the embedding of the second word, which is stick in this case, you would just take the hidden state at the second word at the second time step. You would just take the hidden layer at the second time step from the forward language model and the backward language model. And because that hidden state is actually a contextualized embedding of that word at that time step, so you would just take those hidden states and append them. So you would get a forward context and a backward context when you append them. Yeah.
okay. That's very nice summary. So question: what is meant by a backward language model? Does that mean that?
Right to left.
So that means you give a sentence and you want to predict the word that came before the first word?
uh I believe they train it by giving it sentences in reverse.
Yeah, so let's
Okay.
take it will become it sticks.
Yeah.
Let's.
Okay. So instead of feeding it let's stick to, you would feed it to stick let's and then figure out.
Yeah,
Okay. So it's just a backwards, completely backwards. Okay.
yeah,
Great. So they get these hidden states, which are the contextual, as Gautam said, the hidden states are the contextual word embeddings. That is the embedding of the word now in the context and now transformed to make sense in the context of that sentence. And so that's what these hidden states are. And then you concatenate them together down here. And then the last, so this is what Gautam is saying, you're making use of both the forward and backward the contextual embeddings from both the forward and the backward models. But then this second step here, we're going to multiply each vector by a weight based on the task. And let's see, so these are the original word embeddings that you inherit from word2vec, the green, word2vec or glove. Is that what you understand the green to be, Gautam?
yep, yep. That's what
Okay.
it is.
Okay, thanks very much. Okay, and then, so now, step 2 here is you multiply each of these vectors by a weight based on the task and add them together, and then that gives you the Elmo embedding of that word for this task in this context. So not only in the context of the sentence, but in the context of the task that you're trying to do. So that makes sense from a from an overhead point of view, from a grand scheme of things point of view, but I'm not sure how you get these weights based on the task, how you get this
I
S0,
think
S1.
the people at Allen AI themselves found out that for particular values of S0, S1, S2, I mean, certain specific values of S0, S1, S2 work well for each type of task. For example, for NER, maybe S2, that is the hidden state at second level, is more important than
Mm-hmm.
S1. And maybe for some other task, S1 is more important. I mean, the hidden state at first level is more important than hidden state at 2. So I think tasks specifically, they have found out that certain values work best. So
Okay, so
it's
yeah, go
not
ahead.
trainable. I think you would just choose those values and apply it on whenever you do it.
Yeah,
Okay,
and
so
this
I was thinking you'd have to train them, but I guess you're saying, oh, Alan,
They are like
Alan,
hyperparameters. Yeah.
yeah, Alan already trained these and found out what the good values are for various different tasks. Is that what you're saying?
Yeah. They are like hyperparameters and they have found out good values for those, I think.
I
Yeah.
see. I see. And
and you can begin to see the evolution of NLP in the sense that you can begin to see that the compositional aspects of language are beginning to emerge, meaning that each level in this two-level LSTM seems to point to different aspects of the word embeddings which matter. And you can also begin to see why, for example, an 8-deep transformer is teasing out at each level of the depth a different aspect of the word that becomes important. And this is very rudimentary, it's only 2 levels, but you can begin to see that direction emerge here.
that's interesting, Srinivas. So when we looked at attention, we saw that the 8 different attention heads each attend to different, or can actually be deconstructed afterwards. I guess some people can look at them and say, okay, this attention head is looking at maybe subject-object relationships, and this attention head is looking at I don't know, adverb or adjective concepts, and
Yeah, and there its attention heads at the same level, but again, you have 8, whatever the number is, stack of encoders, right?
mm-hmm,
So this is akin to the stacking of encoders. This is a 2-level LSTM, and then it's stacked 2 deep, whereas when you go to transformers, it's stacked 6 or 8 deep. So slightly different than the heads paying attention to different aspects. It's yet another way to tease out what the words mean in different contexts, because the attention heads that you're talking about are applied to the words at the same level, so to speak, of the encoder, whereas this one is vertical stacking of the encoder one on top of the other, and this is again the stacking of LSTM but just 2 deep.
I see. So that's interesting, and it's interesting. Maybe they were limited by their compute power, and they just said, let's just try the 2 deep and demonstrate proof of concept that it works. I don't know if they tried
I
making
think
more.
though that with LSTM, and that's another thing that the attention helped you get is, I think traditionally all the experiments people ran, you ran out of getting better performance beyond a 2 or at most a 3 deep LSTM. Beyond that, you didn't get very good results. And
Okay.
the attention thing helped you get to a much deeper vertical stack as well.
Okay. So, oops, there it is, back. I lost my microphone for a sec. I'm back now, right? Yes?
Yes.
Yep.
Yes.
Thank you. Okay. Okay, so having gone through and got a sort of a bird's eye level view of what Elmo does with the help of Gautam and Srinivas's comments, we next move on to the ULM fit, and this is something we already know something about. Using transfer learning in NLP, Jeremy Howard and Sebastian Reuter wrote this paper where they showed how using a language model to start with, and then fine-tuning it for different tasks was a good idea, just like it was in computer vision problems. So okay, so now transformer going beyond LSTMs. So the transformer was specifically trained for machine translation. And that's why it wasn't allowed to look forward. Let's see. Then OpenAI came along, and let's see. So it says that OpenAI is trying to do language modeling, and it works with a pre-trained transformer decoder. So does anyone know much about the OpenAI model? Okay, well, we're just going to get a high-level look at it here. I guess the idea is they're just taking remember the stack for the transformers paper, there was a left-hand stack of encoders and a right-hand stack of decoders. So OpenAI just uses the decoder part of the transformer. So that's just this high-level slide. And then going into a little bit more detail, here's the input going through a stack of decoders, and then at the end, a feed-forward neural network plus a softmax that gives scores of all the words in the English language. So it predicts the next word with the one with the highest score. So let's stick to, and then improvisation gets the highest score, and then that gets selected. So we've seen this architecture before. Putting a softmax and allowing it to select allowing it to score every word in the English language, and taking the word that gets the highest score, and that's the output that it predicts. Okay, so let's see. That's the pre-training step. So they take this. So this is what Alan AI does. It trains this OpenAI transformer with a tremendous amount of compute power to be a very good language model, and then it hands it to the community. So you can now download this GPT pre-trained language model, and then apply the transfer learning, as we saw in ULMFit, apply transfer learning to another task. So, and here's the schematic of that. You have the OpenAI model pre-trained, and now you want to train it on spam classification. So you give it some sentences. Again, you put the same top layer, feed-forward neural network plus softmax, but this time, well, it's not the same top layer because now it's only trying to classify two things instead of classifying 30,000 things, which is all the vocabulary in the English language. So it's basically the same pre-trained OpenAI transformer, but you cut off the head and put on a new head with just two outputs, and then you can predict spam. And I guess they tried this with, as Gautam said, they trained it on many different kinds of tasks. So first is a classification task, and that would be the spam or no spam. That would be an example of a classification task. Entailment, I guess, is this idea whether a sentence follows another well, it's more complicated than that. It gives you a premise, and then you have to decide whether premise and hypothesis. So
yeah, that's, I think, otherwise sometimes known as the neural or language inference, which means does the premise lead to the hypothesis or whatever, I forget the exact terms, but bottom line is, can one be reasonably derived or inferred from the other?
I see. Okay, so so it gives you some text, and then says something about what that text means, or
Yeah.
what you can
So
infer from it.
can you infer sentence B from sentence A?
Yes. Okay. So try to think of an example.
It rained yesterday and were the roads wet? So something like that.
Okay. So that's entailment. Does one sentence follow from, or does one piece of text logically follow from this? Does the second piece of text logically follow from the first?
Yep.
Would that be good?
Yeah.
Okay, so that's the entailment task. And then there's a similarity task. You have two sentences going in, and you turn loose a transformer on both of them, and then I guess you can get a score. You can compare the scores and then see if and see how similar they are. So, if you have two sentences about, I don't know, 18th century France, the government in 18th century France, and then compare them, and are they similar? Are they making similar conclusions, or are they somehow similar in structure? So comparing two sentences to another to find out how similar they are, and then multiple choice. I guess that means you give it a bunch of sentences and then you pick the one that's. I'm not sure what the multiple choice task is.
It's, I think, literally answering multiple choice questions that are typically given to students at, if you take your pick of grade N.
Okay, I see. Yeah, so you have context. So you give it you give it a paragraph that asks a question. You give it an answer to the question. You give it the same paragraph to another transformer, and you give it the same context with another answer. Feed that to a transformer. You give it the same context with a third answer, or maybe even n. There doesn't have to be just three. There could be many of them. And then the transformer somehow scores the answers in relation to one another and picks the best one. So that's the multiple choice. I didn't know they did that. That's really interesting.
Yeah, they have results now of saying such, matching a certain level of performance at a certain grade level.
Wow. And so how good are they? Are they up to high school level yet, or?
Don't recall. Uh, that's all I know.
Uh-huh.
But I haven't dived into it. This is the beauty of, or the challenge of NLP is, there are like, and they've just listed 4, but there are so many more, and every one of them has state-of-the-art score and approaches that lead to results.
Yeah. Yeah. So then this is what Gautam was talking about, where each task they train it and they find out what these values of S0, S1, and S2 are that are best for these for each task. And then from then on, they just give you these numbers that are already somehow already pre-trained for you, these hyperparameters. This is what you were saying, Gautam, right?
Yep.
Okay. Okay. So then next, this section, BERT from decoders to encoders. So the OpenAI transformer was based on decoders, but as we said before, the BERT model is a stack of encoders. So what's going on here? This is to add bidirectionality in some way. So then this is the way that BERT is trained. It's the special training method that is the key to BERT's success. They train it with these masks. So they give it a sentence and they mask out one of the words, or maybe more of the words, and then they get it. So 15% of the tokens, I guess, are randomly masked, and so they train this model to guess what these masked words are. And again, the same final layer that we've seen before. It's a softmax layer over the entire vocabulary. And the one with the highest score is the one, if you're trying to find the masked word, you pick the one with the highest score. But the subtlety here is that they're doing a little bit more. 15% it says originally that 15% are masked, but that's not really what happens, is because some of those tokens, instead of being masked, some of the tokens that are selected to be masked are treated differently. Sometimes they put in random words instead of the word that they were going to mask, and sometimes they don't mask it at all. And so there's a little subtlety in the way this goes. I think it's like it tells us in more detail in this understanding BERT part 2. So let's go in here for a second, look at the masked language model. So so here's how it works. 80% of these tokens that are selected, okay, so 15% of the words are selected to be masked, but only 80% of these are actually replaced by the mask token. So only 80% of these 15% are actually masked out. 10% of them are replaced by a random token. So they're not masked, but they're replaced by a random token. And the other 10% were left intact. So here's the example that comes from the paper. So you have a sentence called "My dog is Harry," and you select the word "Harry" as the word to be masked. So what happens is that 80% of the time you replace that word by a mask token, but 10% of the time you replace this word by some random word. My dog is Apple. And then the other 10% of the time you don't do anything, you just leave it there. And so I guess there's a reason for doing this. And this is a nice summary. It makes sense, at least. He says that by sometimes asking it to predict a word in a position that didn't have a mask token, the model needed, so in other words, you gave it, let's see, wait a minute, let me go back for a sec. So I guess this is the question he's trying to answer. Why didn't he just use mask every time? In other words, 15% of the time you select a word and then you replace it with a mask token. And then he's saying, okay, but they didn't do that. They did this other thing where they only used the mask token 80% of the time, and 10% they replaced it by a random token, and the other 10% they left it alone. And then he asked the question, why didn't they just use a mask replacement token all around? I'm sure that, when they did this experiment, I would bet that when they did this experiment, they first tried that. And then somebody thought, oh, let's see if we can make things even better. And then they tried to fiddle with it a little bit more. And that's how they came up with this 80%, 10%, 10% scheme. But he's trying to explain it here. And he says that, 15% of the time, this would make the model learn slowly, since only 15% of the time it's learning something for only 15% of the words. But then by sometimes asking it to predict a word in position that didn't have a mask token, you force the model to learn a contextual representation of all the words in the input sentence, just in case it was asked to predict them afterwards. So I'm not quite sure what that means.
While I don't fully agree, but it seems to imply that that when you don't mask and ask it to predict that word, then it's predicting a word that exists in the sentence, right? Because in those cases, as you saw, the 10 and 10% was it gave a random word or it gave the correct word.
Yeah.
And so it has to learn the contextual representation of all the words in order to be able to predict the correct word that would appear. That's the next 10%. So it can't just learn to say there is a mask there, but it has to learn to also say the exact word that will show up in that position.
Yeah. I see. So you're saying we can't just ask it to predict whether there should be a mask. In other words, it's not allowed to predict mask, right? It's not allowed to predict that the next word is a mask token.
Yeah, and it needs to learn all of the words, because any of the words could be the one that
could be masked. Yeah.
It could be masked, or it could be the word that is actually being asked to be predicted and is the actual word in the sentence for the 10%.
Yes. 10% of the time, right. It's being forced to produce. It's being forced to predict the right word.
Correct.
So that's kind of guiding it.
Right. The 10% of the 15%.
Yes, 10%. So that's 1.5%.
Right. And then the other 10% is it's asked to predict some random word. Now, he can't obviously say why that is done, but he's explained saying, if I always give you a mask, then it'll learn slowly. And if you wanted to predict the correct word, it could be any word that I'm masking and asking it to predict. So that says to the model, you better learn the context of every word, because I could ask you to predict any of the word and have it be the correct word.
Yeah, so I understand why some of the words are left intact, because otherwise the model won't have any guidance as to what, as to how, what it should be doing. But what about the random? I don't understand why it's being confused, why it's being given random words.
Random incorrect words, actually.
Random incorrect words, yeah. And so what it's doing is you're giving it a sentence, but you're substituting a random word somewhere in that sentence, and then you're asking it to predict that random word. I'm not quite sure what.
Yeah. Because first of all, it's the masked 85 or whatever the percent is, and then of that, 15% masked, then 80% and then the subsequent 10 and 10.
Mm-hmm.
Yeah, so the last 10% of that 80-10-10 split is what you said, a random
Is the
word, and
random
then
word, yeah.
and the only thing I can figure is it helps it contrast between random word and the correct word.
Yeah, I would kind of think that it would want to prefer the correct word. In other words, give it maybe 15% correct words and 5% random, but I don't
Yeah,
know why. I don't know
see,
why they
it's
ended up with
the
the
reason that
same.
sometimes I feel these explanations, and I wish the authors would also write, as you conjectured, as to how they got to where they got to, rather
Yeah,
than just this is the result, because
yeah.
the explanations otherwise feel to me like just so explanations.
Yeah, and the paper, I did look at the BERT paper, and um, I, they did talk about that process, but I don't think they gave an exact reason how they arrived at that 80%, 10% formula.
Yeah,
But
how and
anyway,
even
yeah.
why they went down that path.
Yes. I mean, I'm conjecturing that they did it because they got better scores when they did that, but I mean, what made them decide to do it in the first
Yeah,
place?
maybe, or even more interestingly, what made them think that that approach would work? I mean,
Yeah, I
because
mean, I
that gives
understand the
reasoning
masking
behind.
approach. I understand masking words out. That's a great
Right.
idea. I mean,
Yeah.
it's clear that that's gonna be a great idea. But why 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 not use masking all the way through? Why are they just using it 80% of the time, and the other 20% they're doing other things?
No, I
Yeah.
think that part
Kind of.
is clear, right? Uh, like if you were to always replace it with the mask token, then the model would assume that uh, I need to calculate good contextual embeddings only for the mask tokens, since that is the only time I'm being asked to predict anything. So it would not bother to make good contextual embeddings for any of the other words if all the time you asked it only to predict for the mask token. But on the other hand, if you were to ask it to predict for a random word where there's actually a word, then the model is forced to uh, forced to make forced to get the contextual embeddings for all the words as opposed to just for mask tokens. I
Yeah.
think that part is
That's
clear.
right. Yes. It's the contra is the last 10 of random words versus the correct words that I don't quite
Yeah.
get.
Yeah, so why not just give it? Oh, okay, so I understand what Gautam said is that you need to give it, you need to force it to predict the context for all the words. So why not just give it like 80% of mask tokens and then the other 20% the right word, the correct word? Um, that would make sense, but I don't understand
I
why
think maybe
sometimes they
that
put in
makes it
random
too
words.
easy for the model. I'm not sure.
Uh-huh.
It would, yeah, it might be too easy for it to predict.
I see.
Yeah, I'm kind of thinking of this as sort of like regularization, similar to how there is a mix-up augmentation, right? So you like sort of randomly worsen or change what you're predicting.
Yeah, that makes a lot of sense. Because regularization is always like you're going to do something to kick the model and hurt it, in some way, and you just do that a little bit, and then that makes the model stronger or something like that. Yeah, that's a good point. So Yuri, you think that the 10% giving it the wrong word is a regularization method, is a regularization uh,
Like
add-on.
like regularization.
Yeah, regularization like. Yeah, I think that sounds right. Okay. Okay. So back to Jay Alamar. So here he goes through this masking bit, and then he talks about the second step. So that's the first task that it's trained on, is this masking task, mask language model. And then the second task is trained on is a two-sentence task where you give it pairs of sentences, and 50% of the time, the second sentence is the following sentence, is the follow-on sentence to the first, and the other 50% of the time, the second sentence is just some random sentence chosen from the corpus. And then you have to predict the likelihood that sentence B, the second sentence, belongs after the sentence A. So again, it's just a two-way classifier, is next and not next. So then here's what the input looks like. Sentence A, separator, and they have this extra token here to show it, to tell it when there's, when the end of the sentence is. And then they also have this extra token here called CLS, which is to aid it with the classification. It's the CLS token that is put through the final layer to help it to classify the sentence, the sentence B. So that's the second task. So I guess the pre-trained BERT comes already trained on those two tasks. And then I didn't read the last part of the paper very closely, but once they've done this pre-trained model, then they use it, and they show how to use it for other different tasks. And so this is a schematic of say 4 of those different tasks. One is sentence pair classifications, and then they list all of these abbreviations for the tasks in the literature, which is kind of helpful because, in other words, you can see all of these in the paper, all of these in the tables in the paper, but now this makes it clear. It says all of these are sentence pair classification tasks. And then again, SST2 and COLA are single sentence classification tasks. And question answering tasks, we already know about SQUAD. And single sentence tagging tasks, these data sets. And this is like named entity recognition, I guess, where you're trying to find out what each word, you're trying to put a tag on each word as to what kind of a word it is. Is it a proper name, or is it a number or something like that? So let's see. So these are the four types of tasks that they use BERT for. And all of them, sort of the schematics look very similar. The output is a class label. Let's see. Okay, so then that's task specific. You use the pre-trained BERT to solve different kinds of tasks. And then he says, I think this is the last thing he says, the last thing he says is that you can use BERT for feature extraction without even fine-tuning. So he says the pre-trained BERT, which we talked about up here, the one trained on these two tasks, the masked language model and the two-sentence tasks, can be used for, it can be used directly for finding contextualized word embeddings, just like Elmo does. So you do that, you get these contextualized embeddings, and then you can use them in whatever model you're working on. Okay, so what is this schematic? Generate contextualized embeddings using BERT to do that. And then take those embeddings and the output of each encoder layer. Okay, so there are 12 encoder layers, and then each one can be used as a feature representing the token. Okay, so for each,
basically, Joseph, this is akin to the 2-layer LSTM. Now you have 12 layers, and you can weight them differently depending on the task, the embedding that each layer gives you. Which in Elmo you got 2 embeddings, and you did from the first and the second level LSTM, and you weight them differently and combine them with the input embedding. So you had 3.
Yes.
Here you get 12, and depending on the task, you can weigh any one of those 12 embeddings appropriately, and as Gautam was saying, make them hyperparameters and tune them in order to get the best result for that task.
Yes. So here, yeah. So that makes sense. So here's the outputs of the 12 layers. The, the 12 layers, and then for each word you get one embedding, a contextual embedding. So you get 12 different contextual embeddings for each of these 3 words. And then, as Srinivas said, you can then combine them in some way with the original embedding. So there's 12 layers plus the original embedding, just like in Elmo, where there was 2 layers, 2 LSTM layers plus the original word embedding. So he shows, I guess here, different ways of combining the last 4 hidden layers. Just use the second to the last one. Some all 12 layers. Just use the last one. Just use the first one. And then he gives scores, F1 scores. I'm not sure what dev means, but I guess you can see that if you just use the last hidden layer, that's a good score, certainly better than just using the input word embedding itself. But if you sum all 12 layers, you get a big improvement than over just using the last one. If you just use this, but this is interesting, if you just use the second to the last layer, you get even better than if you sum all 12. That's not clear why. And then if you sum just the last 4, you get even a better score. And if you concatenate the last 4, you get even a better score. So that's kind of interesting. I guess this came out of the experiments they did.
I think it's
So
because the
yeah.
last hidden layer was too focused on the previous tasks, that was masked language modeling and the other one. So since it was too focused on the earlier pre-trained task, the second to last hidden layer actually outperforms it for other tasks.
Well, anyway, that's interesting. So as Srinivas says, there are, you get these 12 different contextual embeddings out, and then you can do with them whatever you want to try to see what's best. And so they did a bunch of experiments, and they found kind of weirdly that if they concatenate the last 4 hidden layers, you get the best result among all these different comparisons. I don't quite understand what you said, Gautam, that the last hidden layer is not so good because it was too.
So what I'm trying to say is, I don't know how to put it well. Like, since it's the last layer. I mean, that's the layer that you use to predict the masked language, the masked word, right? So its weights would be very much fine-tuned to that particular task. It may not be generalizable to another task. It was fine-tuned in such a way so as to suit the masked language modeling task.
Okay.
So that's why a layer prior to that would be more useful for a general task.
Okay.
Does that make sense?
Sort of. I have to think about it a little bit more. But anyway, it's interesting that I guess the different ways of combining the layers result in, looks like significantly different scores on this task. So that's the end of what I wanted to do today. And I think the best thing to do next time is to just continue on with this, because he says, unless somebody has a better idea, but so this is in 2000, at the end of 2018, right? So it's almost 2 years ago. But he says the best way to try out BERT is through the BERT fine-tuning with Cloud TPU's notebook that's hosted on Google Colab. So this is a good place to use next, unless somebody knows of a better one where you can just take a Colab notebook and start playing with BERT. Maybe there's a better one that we could use for next week. So let's think about that. And if anybody has ideas, just put them up on Slack. and then we'll figure out what to do next week. But tentatively, what I want to do then is to look through this notebook that Abe refers to, and I'll post it. So BERT end-to-end fine-tuning with cloud TPU, sentence and sentence pair classification tasks. It looks like an interesting starting point. Okay, so unless somebody has a better suggestion for next time, let's just do that one. And so are there any comments or suggestions or anything else?
I've just got a question about the difference between using encoders and using decoders. Like there it said that the GPT model used the decoder. I just thought from the attention is all you need paper that encoders and decoders were basically the same, apart from a decoder took an input from an encoder. So would anybody know what the difference is between using the decoder stage of the attention is all you need model as opposed to using the encoder stage?
Well, I have to say that question threw me as well. So I have the same question as you.
Yeah,
So
because
okay, so one difference is that in a decoder, in the very first attention that you see, it cannot attend to words that are ahead of it. It cannot, I mean, can only attend to the current word or the words that came before it. A
yeah, so it
decoder
uses
is just,
a
yeah,
masking system, doesn't it? But
yeah,
does BERT not use its own masking system? Although it's not masking out the next word, it's masking out random words. Is that
no,
not just exactly the same? But
no, that's something totally different, right? That is just a task that you train BERT for. A BERT, you can think of an encoder is something that just encodes a sentence as a whole to some embedding that you can later on use on some other task. Whereas a decoder is just some sort of word prediction. It's just a language model. If you attach it to an encoder, it's a conditional language model. Whereas if it's simply a decoder on its own, it just takes words one by one and predicts the next word.
But you know, like in the attention is all you need paper, every third layer would be an attention layer that receives an input normally from an encoder. Does that layer just disappear then when the decoder is just used to be a pure language model?
Yep.
Right.
It won't attend to anything from outside. It just attends to itself. It's just self-attention all the way.
Right. And when you're predicting the next word, that's what's called a language model, isn't it?
Yep.
So in the case of BERT, is BERT not a language model then?
Yeah.
Because
It's not
it's
a
not
traditional
predicting the next
language
one?
model. Yeah. It's not a traditional left to right language model. It's a masked language model. It's not the
Yeah,
usual type of language model.
It just generates bidirectional. They call it encoding, but it's essentially another embedding. Actually, it says bidirectional embedding itself. Yeah.
Yeah.
Okay.
Only the task is masked language model, but BERT is just used to generate encodings or embeddings. Yeah.
Okay, cheers, thanks.
Oh, okay, that makes sense. So BERT just generates embeddings, or that's its original. Is that what you're saying, Gautam? That its original use is its output is just going to be embeddings?
Yes,
Yeah,
and yeah, you fine tune it and you just attach another layer at the end. Like if you're doing a sentiment classification or something like that, you just attach that particular thing on top of this BERT, the pre-trained BERT, and you can use it for that. Or if it's an NER task, it will be a different kind of head that you add to BERT. Yeah.
Okay.
it's basically the transfer learning type of approach where you just replace the head and use the BERT embeddings.
And is the GPT one that's different then? It's just purely for classification, is it?
Yeah, GPT is a language model. I'm not sure how they use it for text classification. They probably take the last hidden state, or they combine all the hidden states at all time steps, and they make a softmax over your classes. I mean, positive or negative, whatever. Yeah.
Yep. Okay. Cheers.
And Joseph, to your point, I think the masking is clever because it also helps sidestep this issue of bidirectionality. Because without masking, the bidirectional stuff was harder. But with masking, you don't care which direction you're going in.
Yeah. I mean, with the masking task, it's not cheating to go in the other direction, you know, because the task is just to predict, you know, whatever word is masked out, and you want the whole context of the sentence to do that.
Right.
So that makes sense, yeah. All right. Thanks everyone for sticking around, and hopefully next week we're going to make more progress by looking at an actual notebook and really see how BERT works in a real, you know, in a real task. So tentatively we'll look at that. I'll post this on Slack, the notebook that Jay Alamar points to, but remember that was the good place to go 2 years ago. There might be a better notebook to look at now, 2 years later. But tentatively, we'll look at that one unless somebody has unless we can come up with better suggestions. It's probably not going to hurt to look at the one that Jay Alamar pointed to, which I'll post on Slack. All right, everyone. We'll see you next time then.
Cheers, Joseph. Thanks for that.
Okay.
Thank you.
Bye.